Swayam Prabha. Digital India. Educated India.
Hello and welcome to today's lecture. So we ended the previous day's lecture by observing that if you have a linear time invariant system, right, whose impulse response is characterized by a function such as this, then it is actually easier for us to deal with the Laplace transform of this impulse response, which we call g of s and has a specific name known as the transfer function. Now, why is this the case? Why are we saying that this is actually an easier object to deal with or an easier domain to deal with? So, that is what we shall be talking about in this lecture today. But suffices to say that, once again let me recall that in an earlier lecture we had shown that y is equal to g of u, often we omitted the bracket of course. In this case g was the operator, okay. It was not a product. Even if we wrote it as gu, this did not denote a product. But it turns out that now when you are in the Laplace transform domain, you can write the transform of the output as y of s, and that is nothing but the product of the transfer function and the Laplace transform of the input. In that sense, you can also give another definition to the transfer function. Apart from calling it the Laplace transform of the impulse response, you can also call it as ratio of the Laplace transform of the output to the Laplace transform of the input with all initial conditions set to 0. We shall see shortly what these initial conditions are and why they enter the picture. All right, with all initial conditions set to 0, right. So, that is how we can describe an alternate description of the transfer function, okay. That is an alternate description of the transfer function of g of s. Now, let us revisit the differential equation that we had seen a couple of lectures back, all right. So, I believe it was a third degree differential equation. So, it is a0 y triple dashed plus a1 y double dashed plus a2 y dashed plus a3 y is equal to b0 u double dashed plus b1 u dashed or prime plus b2 u, okay. This is the differential equation, and we assume initial conditions are 0. In other words, y0, y dashed 0, y double dashed 0 are all 0, okay. That is what this assumption entails. In that case, what can we say? Indeed, let us take the Laplace transform of both sides of this particular differential equation. What it leads us then to is the following: a0 s cubed y of s plus a1 s squared y of s plus a2 s y of s plus A3 y of s is equal to B0 s squared u of s plus B1 s u of s plus B2 u of s. In other words, collecting similar terms together, we can write this as A0 s cubed plus A1 s squared plus A2 s plus A3 times y of s is equal to nothing but B0 s squared plus B1 s plus B2 times u of s. Notice how we have reduced a differential equation, the solution of which entails integrations and possibly something called particular integrals in general, right? How we have reduced that problem to one of just some algebra, some algebraic manipulations. We have a polynomial as a coefficient of y on the left hand side and another polynomial as a coefficient of u on the right hand side. So now, if we were to write this in the following form, y of s over u of s, okay, we can write this as a rational function. What is a rational function? A rational function is nothing but a ratio of polynomials. So you see that in the numerator you have a polynomial here, and in the denominator, you have another polynomial, right, cubic polynomial and a quadratic polynomial in the numerator, a1 s squared plus a2s plus a3. Okay. This is nothing but the g of s, or the transfer function corresponding to the system that is described by this differential equation. This is a very, very important result, because this will allow us now to obtain the output y, at least in the transform domain, for any input u, provided we know what the Laplace transform of that input is. What do we need to do? Suppose we know what u of s is, we just need to multiply u of s with gs, and then we would know what y of s is. And then, if we are also given a table of inverse Laplace transforms, we might also be able to find out y of t by taking the inverse Laplace transform of y of s. Of course, we might need to do certain manipulations before we proceed with that. Not every type of function can straight away have a Laplace transform written in a table form. We might need to do some algebraic manipulations, perform some algebraic manipulations before we can get there. Nevertheless, there is hope that just by this operation of division, or taking this rational transfer function and multiplying it with another function, right, and then taking Laplace inverse using a lookup table, might help us in solving this differential equation. Okay. So the solution that we shall get in this way, or the solution that a transfer function will lead us to, is, it's got a very special name. Okay. It's called the zero state solution. Okay. So every differential equation's solution can be split up into two parts. One part is the solution of the differential equation due to initial conditions, right. So if you are taking all your initial conditions to 0 and you are only considering the response of the system to external output, like so, then the transfer function proves to be adequate, and such a solution is called the zero state solution of the system given by the differential equation. On the other hand, if you had taken this input to be 0, all your inputs to be 0, and if you are looking at the complementary function, or if you are looking at the solution of the homogeneous differential equation, then that solution, so solution of the homogeneous differential equation, that is with 0 input, is quite simply called the zero input solution. So if you are looking for the complete solution of a differential equation, right, if you are looking for the complete solution of a differential equation, so the complete solution will be given by the zero input solution plus the zero state solution. Okay. So this transfer function allows us to compute or to obtain the zero state solution. It is assumed that the zero input solution you already know how to solve. Remember in a class on in a lesson on differential equation, you first had to take this complementary function, you had to take a polynomial and just solve for its roots, and you saw that the roots were nothing but of the form something like summation ci e to the power lambda I t, where lambda I are solutions of the polynomial or roots of the polynomial, say a0 s cubed plus a1 s squared plus till a3 is equal to 0, polynomial equation, right. So if you solve for this, you will get 3 roots, of course, which can be complex or real, and then in that case this solution can be described, the zero input solution can be described in this fashion, where you can solve for C1, C2 and C3, because there will be 3 roots, so C1, C2 and C3 using the initial conditions. So in other words, this allows you to simplify the solution of the zero state part of the differential equation, and which is essentially the more difficult part we find. Why? Because the moment you change u of s, this solution, that is the zero state solution, will keep changing. Yeah. So it would be nice if we had an easier way to do that, and this Laplace transform provides you exactly with that easy way of doing it, right. So having seen that, we hope that the motivation for a closer inspection of Laplace transforms vis-a-vis the solution of differential equations is at least clear. Now we dwell a little longer on what we have described as the transfer function and define certain things. So just let me write that down, what I have just been saying so far. It is a transfer function, it is typically a rational function. Hopefully by the end of this lecture we will see some examples of transfer functions that are not necessarily rational functions in S. Okay. Again, to reiterate, a rational function is a ratio of 2 polynomials, alright. So now, one of the things that we want to define is roots of ns is equal to 0 are the zeros of the system whose transfer function is given by gs, and roots of ds is equal to 0 are the poles of the system, where we write gs as n of s divided by d of s, and remember that these are both polynomials in S. Okay. So that is what we call poles and zeros of a system. Throughout this course, these terms poles and zeros, we will be encountering them several times, almost in every other lecture as we move towards more and more advanced topics, right. So it is very important to right away know what poles and zeros are. If you have a transfer function which captures the behavior of a linear time invariant system, then you set the numerator polynomial to 0 and solve for it, right, and you get what are called the zeros of the system. Similarly, you set the denominator polynomial to 0 and solve for that polynomial's roots. Those are your poles of the system. So of course, a word to the wise here, we are assuming for the time being, and of course throughout this course as a matter of fact, that we are dealing with single input, single output systems, okay, for which transfer functions are basically rational functions. You shall see if you take up advanced courses like multivariable controls, wherein you will have multiple inputs and multiple outputs, even though the system might be linear. In that case, a transfer function becomes a matrix of transfer functions, right, instead of being a single entity. And there the order of multiplication, so for instance, we were very lax about this, right, we wrote ys by us. So of course, if these are all, you know, multivariables, you cannot just write ys over us like this, you cannot divide a vector by another vector like this, yeah, it will be rather frivolous description. And there us times gs is not the same as gs times us, okay, so the order of multiplication matters. For the sake of consistency, in this course also we shall pay some attention to the order of multiplication, although for all practical purposes it really matters not. But just to be consistent with the notation that you might encounter in a course on multivariable controls, I shall try to adhere to the order of multiplication, that sort of convention. Okay, so it will always be given by y of s is equal to g of s times u of s, and not, although essentially they will be the same, we will not write this as u of s times g of s. Okay. To reiterate, this is as valid as this if you are dealing with seesaw systems, single input, single output. But for multivariable systems, the order of multiplication matters. For one, you can immediately see that this will be a vector, this will be a vector of inputs, and this will be a matrix. So obviously, the pre-multiplication of a vector by a matrix like so is not the same as pre-multiplying the matrix by a vector. For one, this multiplication may not even be valid. In fact, it will not be valid, right, if it is just a single vector. So we should not be frivolous in interchanging the operation or order of operations unnecessarily. Okay, we will talk more about this in some later lectures as we progress. Right. So a few more observations. Typically, NS is a polynomial of degree m, and ds is a polynomial of degree n, with n being greater than or equal to m. What are n and m? N and m are obviously positive integers. Okay. So typically the degree of the denominator polynomial is greater than or equal to that of the numerator polynomial. When n is equal to m, the transfer function is said to be biproper. Okay. When n is less than m, the transfer function is strictly proper. In most practical systems, you will have transfer functions that are strict. Oops, sorry, my bad. That should have been n greater than m, not less than m. So when n is greater than m, then the transfer function is strictly proper. One of the main reasons is, you note, for instance, a typical case of a transfer function that is improper. That is to say that the degree of the denominator polynomial is less than that of the numerator polynomial, such as this. So here obviously you have a first degree polynomial in the numerator, a 0th degree polynomial in the denominator. So this is improper. So this is an improper transfer function. Now what happens if you pass a unit step through such a system? We know that the Laplace transform of the unit step is basically 1 over s, right? So then what is y? Y is equal to nothing but the Laplace inverse of gs times 1 over s, which is nothing but the Laplace inverse of 1, and this we know is indeed the delta function, or rather the Dirac delta, not call it a function, the Dirac delta. So you see what happens the moment you start introducing these improper transfer functions, even for signals that themselves do not have such Dirac deltas, or in a strict, in a broader sense, the derivatives of those Dirac delta and the doublet function, so on and so forth. Shouldn't really call them a function again. Never mind. You end up getting in your output these Dirac deltas. What's more is the fact that, look, you're giving an input, and this sort of a transfer function basically necessitates the appearance of the derivative of that input in your output. What does that essentially mean? If you want to find out the derivative of a function, ideally speaking, you should know which direction it is headed in time. So if at the time instant t1 you want to find out the derivative of f of t, then you need to know f of t plus h minus f of t upon h limit h tending to 0. What does that mean? That at the instant t1 your output is dependent on some input in the future. So this also violates the tenets of causality, and all physical systems around us, they are all causal, which is why you will not encounter physical systems whose transfer functions are given by improper transfer functions. Yeah? So typically you will encounter at most by proper transfer functions. Later on when we cover state space methods, we will see that indeed for improper transfer functions you will not have a state space representation. Yeah? The state space representation is not equipped to handle improper transfer functions, but we will get to that later, all things in due time. Okay, so having seen this, let us now push for something more. So since we are already talking about the solutions of differential equations here, let us see where we would be without the aid of Laplace transforms. Okay. So take for instance a differential equation given by x dot. So of course earlier I know I used the dash to represent the derivative, maybe in an earlier slide. Yeah, I believe I used the dash to represent a time derivative. Please excuse me for the use of the dot here to represent the same sort of a time derivative. Okay, and we have, let us say, 2x of t is equal to the impulse. So if you are trying to find out the impulse response of this system, what is that essentially? You apply the impulse as an input. Yeah. So if this is your system, essentially this is your system. Yeah. So effectively your system is like, let us say, x dot plus 2x is equal to u, and in order to find the impulse response, what you do is you just apply the impulse at the input channel, right, and what you get as the output is going to be your impulse response of the system, is it not? Now here is where that subtle point which I made in the last lecture about choosing the lower limit to be 0 minus instead of 0 plus, right, in the definition of Laplace transform itself, that will begin to show up. Before we get there, just another motivation. So suppose you take the delta, the Dirac delta for instance. What do you think is the Laplace transform of this going to be if we define this in this fashion, say from 0 minus to infinity, delta t e to the minus st dt. Let us define an alternate way of describing the Laplace transform, which we call L plus, which some books, in fact all books till the 1960s have used to consider this sort of a definition, but now only a few of them consider this definition of Laplace transform. So we are interested in asking the question as to whether there will be any difference between these two. One of the simplest ways to answer, of course you can integrate this and you will find that there is a difference, so leave that as an exercise for you, but another alternate way of seeing that indeed there is a difference between the two is to consider that this delta in some sense is nothing but, the way we have defined it, is basically the derivative of the unit step. Yeah. So if we take the Laplace transform on both sides, right, then on this side, on the right hand side we get, or rather on the left hand side we get, like Laplace transform of the delta t is equal to nothing but, if you are defining using the first definition here, what you find is then the following. You will see you will have s times, what is the Laplace transform of the unit step? It is 1 by s, and minus, what are we trying to find out? The result at 0 minus. Okay, so what is the value of the delta at 0 minus? It is 0. Yeah. So what we get through this, yeah, what we get through this is basically 0. So therefore, rightly as we have inferred, and we have used also in our last derivation here, you see that if you define your Laplace transform to be the integral from 0 minus to infinity, what you get as your Laplace transform of the impulse is along expected lines, which is unity. If on the other hand you take this, right, delta t with the limit changed like so, now what would you get? Of course the first part remains the same, so therefore you have Laplace plus of delta of t is equal to s times 1 by s minus, and here is where the catch is, right. What is the value of the unit step at 0 plus? You see here, why was this 0? Recall we had discussed in the slide that sfs minus f0 is equal to the Laplace transform of ddt of ft. So our ft here is the unit step function, right. So at t is equal to 0 plus, the unit step of course has a magnitude equal to 1, but at t is equal to 0 minus, yeah, so this would be 0 minus or 0 plus according to which Laplace transform you are taking. So what happens then? What we then end up with is that the Laplace transform when the lower limit is 0 minus turns out to be 1, but this turns out to be 0. So it means that if you are taking the L plus, that is this Laplace transform of the impulse, then you are going to get 0. So basically it is as if this function has not existed at all. A moment's thought will tell you this is not so counterintuitive or surprising at all. Why? Because if you are trying to solve for this, essentially what you are trying to see is the effect, right. See, in a differential equation you will be always given initial conditions to solve, but what initial conditions are generally given to you? The initial condition before the application of the input. So if your input is applied at 0, you can only have knowledge about the initial condition at 0 minus. What happens at 0 plus is no more a known commodity to you. If there has been some change at t is equal to 0 in the input, then the effect of that change in input, that non-trivial change in the input at t is equal to 0 will have to be accounted for, right. So that is why L minus, or this L that we conventionally define as the Laplace transform, and the L plus where the lower limit is 0 plus, these two will lead to two different Laplace transforms for the impulse itself. And now we cast our attention back to the differential equation at hand. Suppose we want to solve this in the classical method. What do we do? So then we consider that, again let me rewrite this. So we have, for example, we have x dot plus 2x is equal to delta, alright. So we have x dot plus 2x is equal to delta. So for t greater than 0, 0 plus let us say, what do we have here? For t greater than 0 plus, we have this equation reduces to x dot plus 2x is equal to 0. Why? Because the impulse has ceased to be, it is an x impulse, okay. So therefore, we can easily solve for this, but when we solve for this, remember, we have to write the solution in terms of, in fact it is pretty straightforward to solve, and you can see that we have to write the solution in terms of the value of x at 0 plus, okay. You can check that this is the solution. The question is, who is going to tell me what this quantity is? Because remember, this quantity came into being only after the impulse has acted on this system. At best, I can have knowledge about x at 0 minus before any input or the impulse has acted on the system. But once the impulse has acted on this system, that results in some value at x 0 plus, at t is equal to 0 plus. So this is a value that I have no idea about. In order to obtain this value, I have to argue along certain lines. What is that line? That line is that I will say that look, this function has a derivative here, the highest derivative, yeah, must match up to this delta. So the highest derivative is the first derivative, that must match up to this delta, and therefore its integrals will be smoother functions, right, relatively smoother compared to this delta here. So I equate this x dot to delta, and then I carry out this integration. Notice very carefully the argument here. We have to make this subtle argument that the highest derivative on the left hand side must equal the highest derivative of delta or delta itself. Here delta itself appears, no doublet or triplet or higher derivative of delta appears. So I equate the highest derivative of x with the highest derivative of delta. So here in this case, I will just say x of 0 plus minus x of 0 minus, sorry, 0 minus, that is, yeah. So x of 0 plus minus x of 0 minus is equal to nothing but, if I integrate between 0 minus and 0 plus, this delta t. So this is the argument that I have to bring in, and now if someone tells me what the initially relaxed value of x is at t is equal to 0 minus, using this integration, so this turns out to be nothing but, it is just 1, right, this is just 1. So if x at 0 minus is equal to 1, then solution is xt is equal to 2e to the power minus 2t. Why? Because x 0 plus is equal to 1 plus this one, you bring this 1 to the other side, so it becomes 2. So this is the solution, okay. So remember what we had to do, we had to actually equate the highest derivative of x, because that could be the only one that could match up to delta or its highest derivative on the other side, right. And then we said that we equate the highest derivative of delta on the one side with the highest derivative of x on the other side, and then we found this, okay. So we had to bring in this argument. Already you can see that this is not a very simple process, right. So this is the classical method of solving it. How about if we use the L plus to solve for this, like people used to do till the 1960s maybe. So what do we do then? So L plus of f of t, just to sort of point out, is nothing but 0 plus to infinity f of t e to the minus st dt. So how about if we bring this idea in? Will this be of much assistance to us? Let us see. So we have x dot plus 2x is equal to is equal to delta, is equal to delta of t, right. I have dropped this argument t for the sake of brevity, you can say it is inconsistent, that is okay, yeah. Now what do we do? Let us say we apply this transform, so we get, upon applying the Laplace transform, we get s times xs minus x at 0 plus 2 times x of s, yeah, is equal to 0. Why 0? We have already seen this, right, that if you take the L plus transform of the impulse, that turns out to be 0. We have seen this here, haven't we? So therefore, we just equate it to 0. Sorry, that has gone off. So it is equal to 0. Now, upon simplifying and rearranging these terms, what we see is that x of s becomes equal to 1 over s plus 2 plus x0, sorry, that was, it is just x naught over x naught at 0 plus over s plus 2, and we are faced with the same conundrum, which is who is going to tell us what x0 plus is. What do we do then? It turns out we have to again resort to the same argument that we resorted to when we were solving it in the classical manner. So then what is the point of all this, right? And you would be right to question that. Indeed, if you are using L plus and if your input has some such impulse, yeah, on the right hand side of the differential equation, then this is the problem that you will always face, always encounter. So again, using the same argument, you have to derive that indeed x0 plus is 2 given x0 minus is 1. So it turns out that the main benefit of Laplace transform, which is to bypass the classical method, is rendered meaningless here. On the other hand, if I were to use L minus of ft, which is basically our conventional, so let me get rid of the minus, because this is the sense in which we will understand our Laplace transforms for this course. Yeah. If we use this definition of the Laplace transform, does it help? Well, coming from this, let me take the usual Laplace transform, let me call it not the L minus but conventional Laplace transform. What we will then have is xs minus, but now we will have x of 0 minus plus 2 xs is equal to 1. So far we have not needed the use of any such argument like in the previous case. And what do we get after this? Right? So we can write, again after simplifying, we can write this as 1 over s plus 2 plus x 0 minus over s plus 2. Okay? And we are done, because this is a known commodity to us. Remember that we know this. This is known to us, and therefore this helps. Okay, that is the key thing to remember. That is the reason why we focus so much on this lower limit of the Laplace transform being 0 minus instead of 0 plus. This is where it all starts to make a huge difference. Okay, so I want you to remember this, and henceforth whenever you talk about Laplace transforms, to always define Laplace transforms in this fashion, the one-sided Laplace transform, that is. Okay. Alright, so having seen the utility of Laplace transforms, it now brings us to the next question as to how do we get the inverse Laplace transform of this. Of course, for simple things you will get the inverse Laplace of these functions in a table at the end of any standard book. But what if things don't look so simple? What if these functions are not in the standard form? Can we somehow push them to the standard form? That is where the techniques of inverse Laplace transform prove to be useful. Okay, and we will see a few properties of inverse Laplace transform first. We have obviously seen them in the slides, we summarized them yesterday, but today we will just go through them in some more detail and maybe derive a few of them. Okay, I will go over these a little quickly and I will leave the rest to you to sort of join the dots. You know, it is basically a bit of integration here and there. So suppose you have f of s, which is the Laplace transform of f of t 0 minus to infinity e to the minus st dt, right? Okay, have I defined it in the right manner here? Yeah. Okay, so 0 minus, I haven't missed that, good. Right, and then we call this as the Laplace transform of ft. Okay, this is how it is defined. Then it turns out that f bar of s, yeah, is equal to, let us say, the Laplace transform of e to the at ft. Okay, that is given by you just know this Fs, you just shift it. This is called the complex shift property. You just shift it by A. How do you prove this? Very simple, just apply this here. Just plug in f of t times e to the at, and then you absorb the A with this S. So you will have minus of S minus A times t, okay? And that is all there is to it. It is very straightforward. So it is a simple exercise for you to check. The second property, before that we will take this integral. Let us define an integral I of k, subscript k, like so. So 0 minus to infinity t to the k e to the minus st dt, alright, and we will do this integration by parts. So you will see that this, if we integrate by parts, we keep this part fixed. So this is u, this is dv, so we get e to the minus st upon minus s, the limit taken from 0 minus to infinity, minus of integration of this same thing then, and you have to differentiate this t to the k. So which is k t to the k minus 1 e to the minus st dt upon minus s, 0 minus to infinity. This is just integration by parts, okay. So this minus and minus will combine to give you plus in the next step, right. And you will see that this part, when t tends to infinity due to the exponential it vanishes, when t tends to 0 minus due to the t to the k it vanishes. So this part contributes 0 overall. So this then turns out to be nothing but k by s times I of k minus 1, which is a recursive relationship, right. So from this, if you know what your I of 1 is, which is nothing but integration 0 minus to infinity, yeah. If you know what your I of 1 is, or rather you can start with I of 0 for that matter. I of 0 is pretty obvious, straightforward, isn't it? So it is just t to the power 0, so it is e to the minus st dt, yeah. So we know what this is, we know that this is 1 by s. So you know I0, you know the recursive relation, combining these two, so this is 1, or rather this is 2, and this is 1. So combining 1 and 2, I of k turns out to be nothing but the factorial of k divided by s to the k plus 1, okay. This is an important result. Why? Because this will help us in finding the Laplace transform of this and relating it to the inverse Laplace transform which appears in this form. So combining these two properties, it turns out that we will be able to go a lot further than what the table might suggest, okay. Right. So without further ado, let us take the generic form of a transfer function, a rational transfer function like we have taken in this case. So you have, for example, a numerator polynomial ns and a denominator polynomial which without loss of generality we can write in this following fashion: I is equal to 1 to k, right, s minus pi to the power r pi, okay. What does that mean? There are basically k distinct poles, okay, where of course we will say that pi are k distinct complex numbers, okay. There is a reason why we have only factorized the denominator and not the numerator in this case, alright. And from this it follows that the degree of ds is of course nothing but this particular polynomial, yeah. So the degree of ds is nothing but summation r pi I is equal to 1 to k. So we are admitting the possibility that some of these poles might be repeated rpi times. So the ith pole is repeated rpi times. If it appears only once, then it is rpi is 1 for that particular pole pi. If it is repeated, let us say twice or thrice, then rpi will be 2 or 3 accordingly. But the total sum of the number of poles with the repetitions is equal to the degree of the polynomial, which must be equal to n as per our description, Remember, we have defined m to be the degree of the numerator and n to be the degree of the denominator. So then this we can generally expand in partial fractions in the following manner. We write this as I is equal to 1 to k, and then each individual term we can in turn then write as, let us say, di is equal to 1 to rpi. I will explain this notation shortly, just bear with me. Ai di, okay, divided by s minus pi to the di, okay, where of course ai di, so these are both double subscripted, it is a complex number, okay, belongs to the set of complex numbers. Of course, pi's are also k distinct complex numbers there, right. So this is basically how we expand things in partial fraction form. What we are saying in other words through this expression is that you will get k such terms. The first summation says that you will get k such terms, and each of those terms is related to one of those distinct poles. Now if you consider each of those distinct poles again, yeah, then they can further be expanded. So for example, if you have some pole appearing twice, then you will have s minus pi squared. So you will have ai1 over s minus pi plus ai2 over s minus pi squared. That is what this means. So quickly, if we take an example, it will be clearer. But before we go to the example, let me tell you why we are interested in writing in this form. Because now notice, by combining these two properties and looking at the Laplace transform, so you see, if you know that t raised to the k has a Laplace transform given by this, and if you shift in the frequency domain, that is if you shift this s to s minus a, it is effectively the same as multiplying the time domain function by the exponential e to the at, right. So combining these two, it is then quite apparent that each of these terms, when you take them, pass them through the Laplace inverse, they will take the following form, nothing but ai di and t to the di minus 1 over factorial di times e to the pit. So then if you have expanded this g of s in this fashion, you will only be dealing with time domain terms such as these, because you take, because of the linearity of the Laplace inverse and the Laplace transform itself, you can take piece by piece Laplace inverse of each of these individual terms, and the Laplace inverse of any one of these terms takes this form. So once you have, as a matter of fact, written this transfer function in this form, the job of writing the Laplace inverse or taking the Laplace inverse is simplified, because you just have to take this into account. Of course, if you are not happy with the appearance of complex numbers as your coefficients, you can combine them in different ways, we will get to that shortly. But for all practical purposes, this ends your solution. So if you leave the solution in this form, it is still a valid solution, okay. Unless someone says that no, you have to only write it in terms of real coefficients, then you have to probably make some changes. Otherwise, this is it. Given a GS, if you want to take its Laplace inverse, this suffices. That is the point I want to make. Now quickly, let me take an example here. So how do you actually go about this business? Because often the way we define things, you see, if you recall the definition of the Laplace inverse, it appeared pretty intimidating in the slide that I had yesterday or in the previous lecture, right. But now, do we actually use the definition? Of course not. We look at the lookup table. So let us take a quick example, something like s over s squared plus 3s plus 2. So I am factorizing this in the same fashion by the same token like this. So it turns out that luckily here there are no repeated poles, So we write this in this fashion. You can check. So I am going over this a little quickly. And now we want to evaluate these terms ai, di. So let me call them just k1 and k2. Yeah, k1 over s plus 1 plus k2 over s plus 2. What is the central idea? Now in a lot of textbooks you will find a lot of methods and techniques, and you might often feel that, okay, if I have forgotten that method, my goodness, how am I ever going to do this Laplace inverse? Let me tell you a trick here. Let me tell you, it's not really a trick. What you are basically doing is this: you are writing s over s plus 1 into s plus 2, and you are writing this as k1 over s plus 1 by plus k2 over s plus 2. So if you multiply both sides by s plus 1 into s plus 2, what you will then be left with is k times s plus 2, k1 times s plus 2 plus k2 times s plus 1. Now this is an identity, right? This is identically true for all s, alright. So what clever manipulation you do here is, turn by turn you want to eliminate, right? So for example, if you had a solution of a system of equations given by ax is equal to b, we know that diagonalizing that system, okay, getting into a diagonal form is the easiest form. So we take this LU form, and we try to solve for this, right? Because we know that the diagonal forms are easiest to solve. So we do some row manipulations and we get it to a diagonal form. This is from linear algebra, basic linear algebra. In the same fashion here, if you want to get decoupled equations from this, so first put s is equal to minus 2, and you get minus 2 is equal to k2 times minus 2 plus 1, and then put s is equal to minus 1, and then this term vanishes. So you will get k1 times minus 1 plus 2 is equal to minus 1. So from this you get two decoupled equations in two variables, that is two unknowns, and you can solve. What you are essentially doing is you are equating coefficients on either side. You are equating the coefficient of s and you are equating the constant coefficient. So if I write this in the general form, right, I would be writing k1 plus k2 is equal to 1, and then I would be writing 2k1 plus k2 is equal to 0. Now obviously solving this system of equations is, even though it is two variables, is little more complicated than solving this system of equations, wouldn't you agree, right? And I urge you to check that the solutions indeed turn out to be the same, which is k1 is equal to minus 1, k2 is equal to 2, right? So you see that this gives you an easy way. So what your textbooks always do is they multiply this on both sides by this, and then they pass it through the limit s tending to minus 2, limit s tending to minus 2, limit s tending to minus 2. Obviously then what happens is this term vanishes, this term becomes minus 2, and you are equating this. So that is how you get this equation. Then if you pass it through the limit s tending to minus 1, you will get the second equation. So even if you forget all those tricks and techniques, you always have this at your disposal, right? Of course you might argue that with a greater number of variables this becomes more cumbersome, and I would agree. So clearly if you remember this, or even if you do not remember this, it is pretty straightforward. Essentially you have to remember that this is just equating coefficients and nothing else, nothing beyond that. Alright, having seen that, so that you do not feel that I am really having an easy example to solve for myself and then leaving you with the more difficult ones, let us take some slightly more complicated example, alright. So let us take an actual differential equation, plus 2x dot plus x is equal to 0, and let us say x dot 0 is equal to b, x dot 0 minus to be precise, and x 0 minus is equal to a. So now again we use the same technique of Laplace transforms. So s squared xs, I am not going to really, okay, x naught minus x dot 0, okay, that is the Laplace transform of this term. Then you go for the second term, plus 2 times, right, then you get 2 times s of xs, yeah, and then you have minus 2 times x of 0 minus. So that second term comes from the Laplace transform of this, and finally you have x of s is equal to 0. So quickly I will just collect together terms on one side and you can check that this is indeed so. We can just plug in these initial values and we will get the following expression: as plus 2a plus b upon s plus 1 whole squared, right. Now you might wonder, what am I going to do? How am I going to find out the Laplace transform and the inverse Laplace transform of this, right? Because now this can be written in the following fashion as a1 by s plus 1 plus a2 by s plus 2, sorry, s plus 1 squared, I am sorry. Yeah, that is the standard form, alright, because it is repeated poles now. So this will only have this sort of a partial fraction expansion, you can check. But now it turns out that this technique I used earlier will only carry me so far, in the sense that if I multiply by s plus 1 squared on both sides, it is all well and good. So I get s plus 1 squared times xs is equal to a1 times s plus 1 plus a2. So if I pass it through limit s tending to minus 1, I will be immediately able to solve for a2, right. So I will get from that, as a matter of fact, I will have this a2 is equal to, so this is minus 1, so it is minus a, so it is a plus b, check that, alright. But what about a1? Is there any trick? Because if I multiply only by s plus 1, I cannot pass it through the limit. If I pass it through the limit, then I will still be left with 1 s plus 1 in the denominator of xs, which clearly does not help. So am I at my wit's end? Of course not. The reason being that if you remember what we were trying to essentially do, we were trying to equate coefficients. So what have we got on the left hand side? We have as plus 2a plus b. Once you have multiplied it by s plus 1 whole squared, which is the whole denominator, just like we did in the previous case, remember, nothing special. We had this whole denominator, we multiplied both sides by this denominator. So on the left hand side we were left with only s. Why not use the same trick here? So we have on the left hand side just the numerator, and on the right hand side we will be left with a2 plus a1 times s plus 1. Now of course from this we already know, right, from this we already know a2. So we can use that knowledge of a2 here and substitute it here and then equate the coefficients, right. So then you will get a1 is equal to a, okay, check. So check that a1 turns out to be equal to a. On the other hand, even if you did not have that information, from the other side, let us say you just blindly multiplied both sides by s plus 1 squared, right, and just equated coefficients, what would you get? You would actually end up getting a1 is equal to a, that would have been easy, and you would have had a1 plus a2 is equal to 2a plus b. Not so bad, is it? So even though this system is not diagonal, it is close to a diagonal, it is a triangular system. So in this case it turns out that we are not at our wit's end, as long as you remember that the key to finding the inverse Laplace transform is nothing special other than just equating the coefficients, alright. So we will continue with some more examples in the next lecture and hopefully be able to convince you by the end that it is really not a big deal to find the Laplace inverse and its and the consequent solution of the differential equation that we are looking to solve, even when poles are complex, unlike the real poles that we have chosen here. Thank you all.